So this is the third tutorial. I think that this little series will be about 5 or 6, so that's 2.5 hours or maybe 3 hours. I'm working my way towards a unit where by the end students are able to solve systems of equations algebraically, or they can do them graphically. They have a feel for why the graphical approach works and why the algebraic approach works. And so far, we've seen two lessons in the first video, getting the concept of equations that have x and y in them and graphing those equations. 3 was more graphing but more complicated, and 4 was graphing two equations to get solutions to a system of equations. In this video, we're going to look at the fifth. Now the fifth lesson is not going to involve graphing. We're going to get back to graphing though for the all-important 6th lesson. But the 5th lesson is going to be the substitution method. That's where one of the equations is going to be given in y equals form, and the other equation isn't. 3x plus 5y. You want to make up a question that has a nice integer answer. All you have to do is, say y equals 2x plus 5, pick the answer, make anything you want for x, 3, and then y is going to be 2 times 3 is 6 plus 5 is 11. So 3 comma 11 is going to be the answer. Then you can plug the 3 and the 11 into here. 3 times 3 is 9. 5 times 11 is 55. 55 plus 9 is 64. So that's a good example of a question. And lesson 5 is important. We'll say that when we have this situation where one of the equations has the y already isolated, the substitution method tells us to replace the y in the other equation with the expression that it's equal to. Now we have to distribute the 5 through, combine like terms, subtract 25 from both sides. A lot of good algebra skills needed to be able to do this. 39, cross your fingers. You'll know that it's probably right if this becomes an integer, which it does. X equals 3. Now to get the y value, you have the choice. You could either plug the 3 into either of these two equations, but this top one's going to be, and that's a good question you could ask students, which equation would you rather plug the 3 into? And the answer is into that first equation, a little bit easier. Y equals 6 plus 5 equals 11. And that is what the two answers were. So this is a great method, the substitution method. You will want to also, let's go again with y equals 2x plus 5. I'll even stick with the answer of 311. But you definitely, 2x minus 3y equal, you definitely want to have one with a minus here. So 2 times 3 is 6. 6 minus 33 is minus 27. So this question is a little bit harder because when you substitute the 2x plus 5 in place of the y, you have to distribute the negative. Actually, let me go like this. I like this to be minus. So then it's not going to be 311 anymore. It's going to be 31. And this isn't going to be negative 27 anymore. It's going to be 6 minus 3 is 3. And this is going to be a minus here. So this is an important question to do. I mean, I would first do one that did have a plus here, but eventually you're going to want to do this kind because one of the more common mistakes in high school math is to not distribute properly. Negative 3 times negative 5 is positive 15. But if they do that all right, subtract 15 from both sides, x equals 3, and y equals 2 times 3 minus 5 equals 1. So definitely you want to do a day on the substitution method, and you could even, on that day say, what if it's like y, plus 2x equals 5, and 3x, I'm just making up stuff now, equals whatever. And they might say, well, we could use the rules of algebra to rewrite this as negative 2x plus 5. And we could do ones, I suppose we could even go 3y plus 2x equals 6, and 5x plus 3y equals whatever. And say even in this one, it would be kind of annoying, but we could minus 2x plus 6 divided by 3, y equals negative 2/3 x plus 2. It might be inconvenient to do that. Actually, now that I've noticed that, maybe before we do this, after we've done this one and this one, maybe we should do one where it's y equals 2/3 x plus 5. For this one, I'll pick a multiple of 3 as my x value, so like 6. That way I get 9. Then I can say 2x minus, be easier if this thing's a multiple of 3 also. I'll just say minus 3y. That's 12 minus 27 is minus 15. That's a fine question to do also. 2x minus 3 parentheses 2/3 x plus 5 equals negative 15. Distribute the 3, you get minus 2x plus 15 equals minus 15. I feel like something went wrong here. Oh. No solution. Interesting. Make that into 6. Two x is 2 times 6 is 12, minus 54, minus 42. Maybe this will work out better. I'm not addressing the whole like multiple solutions or no solution until like basically the last lesson. I don't find that to be like a really important thing at this level, but it is going to be worth mentioning at the end. Let's continue with this. 6 times 2/3 is negative 4x. Negative 6 times 5 is negative 30. Equals negative 42. Something went wrong here. Minus 2x. Maybe not. Minus 2x equals negative 12. Oh, x equals 6. Actually, it is okay. Then you can plug the 6 back into this equation. Gives good practice with fractions. 2/3 times 6. I like to go like that. Okay. So this would be really good for the 4th day. The 5th day, I mean. But the 6th day, this is going to be a really important day. Because I want to build up to the elimination method, which is really the most popular way to answer systems of equations. But I'm going to save elimination method for day 7. Why not just do it on day 6? Well, let's see. Let's go over what we do when we do 3x minus 4y equals, make up an answer, 2, 1. Keep it simple. 2 times 2 is 4. That becomes 7. And here, 6 minus 4 is 2. So here I have a system of equations. And the general method for solving a system of equations that we're going to do on day 7 is that we try to get it so these two coefficients are opposites, or these two. I like if one's positive and one's negative to make those. So I would need to find the least common multiple of 3 and 4, which is 12. And I'd multiply both sides of this equation by 4 and both sides of this equation by 3, get 8x plus 12y equals 28. 9x minus 12y equals 6. Now when I add those two equations together, 17x, these cancel out. This becomes 34, x equals 2. Plug the 2 into either of these equations. 2x plus 3y equals 7, 4 plus 3y equals 7, 3y equals 3y equals 1. So you might say, why don't you just do that? It's a great method. Elimination. Well, the reason I'm not just going to do it is because there's a lot of mysterious things that happen. Like, who says you could just multiply both sides by some number? And who says you could just add together two equations, and when you add them together that sum is somehow relevant to solving the system of equations? Most textbooks would not do this mysterious lesson 6 I'm talking about. They would skip to lesson 7. Only because I was making this series of videos did I even think that there's a really nice and really, really important lesson 6, really important sort of mathematically speaking, and it gets people thinking about, like mathematicians. It's so important. I'm happy I did this series of video just so I can show you what my lesson 6 would be. And this is a tricky lesson, lesson 6. Let's see. For lesson 6, I would want to first examine the solution set to a two-variable equation, 1, 9, 2, 8, and so on. And I would want to then compare it to what would happen if I multiplied both sides of the equation by 2 or both sides of the equation by 5. And I want to have students think about what happens when you multiply both sides of the equation by something. Well, they would, by messing around, realize that the solution set is unchanged. And that's a really good opportunity for the students just to say, like, here are 3 equations, what do you notice? And the thing to notice is that the solution set for all 3 are the same. So when you take an equation and multiply both sides by a constant, you do not change the solution set. And while we're at it, that must mean that the graph, x plus y equals 10, is the same as the graph of 2x plus 2y equals 20, is the same as the graph of 5x plus 5y equals 50. It's kind of interesting. It may not seem that important, and it's not something that, but the reason I'm doing that is because that's a step in the classic way of solving systems of equations, that you multiply both sides of one or both equations by a constant. So this is the thing that allows us, we're permitted mathematically, we don't just do it because it works, we do it because we're allowed to. We don't break any math rule when we do that. So that's something I like. Over here, more about lesson 6. I could ask questions like, if 2x plus 5y, let's 7, 2. If 2x plus 5y equals 24, has 7, 2 as a solution, what is a solution to 6x plus 15y equals 72? And if someone notices, oh, this is triple, this is triple, this is triple, that would mean it also has that in its solution. So that's a sort of thought-provoking question that you could ask on this topic. Okay, so that's only part of lesson 6. The real hard part about lesson 6, and like I said, this is not a lesson you've ever seen before, I don't think. This is just not. People skip over this lesson 6. I'm inventing it right now. Maybe other people rationalize or justify the elimination process with some kind of idea like this, but I haven't done it that much. I've taught this topic, but it's totally needed right here. Here it comes. I think first I would say, if I have two mathematical equations that are both true, those are both things that are true. And when you add them together a piece at a time, you get 5 plus 8, and you get 13 on the right. And if these two things are both true and you add them together, that new equation is going to be true also. So that's kind of surprising. I find it interesting. But what about a two-variable equation, like x plus y equals 10? Well, that's not true or false. That's just like a thing that's true for some points and true for other points. One of the points it's true for is 4, 6. Okay, here's another equation. 2x plus 5y is 38. So here's two different equations. This equation has a whole bunch of solutions, including 1, 9, and 2, 8, and 4, 6, and a bunch of other things. And this thing is a solution set also that has, for instance, 19, 0, and a bunch of other things. 0, 38 over 5. These two equations have very different solution sets. And if I graph them, they would be different lines. But if I did graph them, they would intersect, and they'd intersect at the point 4, 6, because 4, 6 happens to be in the solution set for both of them. Maybe something like that. So if you were to graph them both, they'd intersect at 4, 6. So 4, 6 happens to be the solution to this equation. It makes both equations true. So here comes the big concept. The whole purpose of lesson 6 is right here. What if you add these two equations together? Well, you get 3x plus 6y equals 48. Well, that's a totally different equation. Now, it's not that these two are true and that it's not like before where I took two true things and added them together to get a true thing. Here I took two things that are true for some points and false for other points and added them together and get this third equation. What's so special about this third equation when you add two equations together? Well, you could go ahead and graph it. So 0, 8 and 16, 0. And what you would find out is that new line, whoops, I drew it on top of one of those. It would not be on top of one of the others. There'd be three different lines, but the key is they would all intersect at 4, 6. Actually, this is a good opportunity to bring up Desmos. Let's see if I can do that. I'm not able to get Desmos up on my thing right now, but it would be pretty neat to actually graph these two things beautifully on Desmos and then graph the third one and see that they don't have a lot in common, but they do have that in common. And this basically means, what I like about this is that I can justify why this new equation is going to have 4, 6 as part of its solution. Because if I take the 4 and 6 and substitute them for x and y, 4 plus 6 equals 10. That's true because 4, 6 is part of the solution set of this first equation. And 2 times 4 plus 5 times 6 equals 38. That's true because 4, 6 is also part of the second equation. So when I add these together, it's kind of funny. It's like I'm treating the 4 and 6 like variables now. So 1 times 4 plus 2 times 4 is 3 times 4. And 1 times 6 plus 5 times 6 is 6 times 6 equals 48. So what I'm getting at is that when you add together two equations, the third equation, the result, the new equation, will have in its solution set the point, if there is one, that's common to the solution sets for the first two. And it's kind of surprising, but I hope that, but I find it's really thought-provoking. It's going to lead us to seeing why the elimination method, like why that works. I could make up a question like this. X plus y equals 7. Let's say the answer is 5, 2. 3x plus 5y equals, that's 25. And maybe I say the solution to this system of equation, just tell you the solution is 5, 2. They can verify that. And then say, what is a solution to 4x plus 6y equals 32? And the answer would be 5, 2 also. While we're at it, if I take each of these equations and I multiply them by a number, so I say 2x plus 2y equals 14, and 9x plus 15y equals 75, and add those together, 11x plus 17y equals 89. So I might also, this is an interesting question, x plus y equals 7, 3x plus 5y equals 25. I tell them it has a solution of 5, 2. And then I say, what is a solution to this? And I kind of show them where he came from. So you say, wow, that looks like a really hard question. But if you notice that this is just the top equation multiplied by 2, both sides, which means 5, 2 is a solution. One is in the solution set of the top equation, because multiplying both sides doesn't change the solution set at all. And if you notice, the bottom equation is this with multiplied by 3 on both sides. So it is 5, 2 as one of its many elements of its solution set. And then I say, oh, well, the 11 is just 9 plus 2, and the 17 is 2 plus 15. So that would mean that 5, 2 would have to be a solution. There's many solutions to this bottom equation, but one of them is 5, 2. We can even check that 11 times 5 plus 17 times 2 equals, I hope, 89. 55 plus 34 equals, I hope, 89. 89 equals, check 89. So this is a kind of abstract concept. I doubt you've ever seen this idea that oh, adding together, maybe you have, adding together two equations produces a third equation who has a totally different, almost totally different solution set, but that solution set is also has the solution to the system of equations in it. But how useful is that? Not really. I mean, yes, this thing has the solution in it, but it has so many other things. How does that help us at all? Well, I could put it off for day 7. Maybe I'll tease a hint here. Let's say the answer is 5, 2. So 15 plus 10 is 25. 10 minus 10, let me make it 5, 3. 15 plus 15 is 30. And 10 minus 15 is negative 5. So now we say, well, I don't know that the solution is 5, 3, let's say. And I add them together. And it becomes a new equation, which happens to just be 5x equals 25. By chance, these two things happen to cancel out. So what? It means that wherever these two things, whatever the solution set happens to be, which is 5, 3, but let's say they don't know that yet, this thing will also go through that same point. Well, this 5x equals 25, which is the same thing as x equals 5, goes through an infinite number of points. So is that helpful? Well, yes, it kind of is, because those points, unlike the slanted line, unlike 11x plus 17y equals 89, the equation x equals 5, even though it also goes through an infinite number of points, all those points have something in common, 5, 3, 5, 2, etc. So we can say that the x-coordinate of the solution is 5. Now, this bottom equation isn't so useful anymore, but once we know that the x-coordinate is 5, we can come back to either of these other equations and say 2x minus, 2 times 5 minus 5y equals negative 5. 10 minus 5y equals negative 5, minus 5y equals negative 15, and y equals 3. So that's how that works. But you got to get pretty lucky for that to happen, because that can only happen if these two things happen to be the same sign with opposite, same thing with opposite signs. So maybe we're not so lucky, but if this lucky thing happens, we're able to actually fully complete the question. Again, 5, 3 is over here, and these two things intersected there. All three lines intersected there. But that third line is very useful because it has no y in it, which means it's a vertical line, which means every point has x equals 5, which means whatever the ordered pair is, it's 5 something. And once we know that, there's only one point on this line that has 5 as its x coordinate, and there's only one point on this line that has y as its 5 coordinate, and it is 5, 3. So I'm very excited about lesson 6. I've never seen it before, and I just thought of it in preparing this series of lessons for you. You could skip that lesson, but I think you'd be missing a good opportunity to have some like real thought-provoking questions, and it's going to motivate lesson 7 that's coming next, which is going to be the elimination method, the famous elimination method. But now we have a motivation and justification for why we're allowed to just do that stuff and why we would want to. Okay, well, that's probably the best part of this series, but I think you'll want to see like how does this flesh out with lesson 7, 8, 9, and 10. So see you next time.